Welcome to qnawire.
In this problem, we have a combined gas steam power plant. It has a net power output of 280 megawatts. The pressure ratio of the gas turbine is 11. We have air entering at 300 Kelvin and entering the compressor at 300 Kelvin, entering the turbine at 1100 Kelvin. Combustion gases leave the gas turbine, then are used to heat the steam. Then steam is at 5 megapascals, and we heat it up to 350 degrees C. Combustion gases leave the heat exchanger at 420 Kelvin. You have an open feedwater heater in the system, so that that's basically allow. We have stuff kind of recycling back. So then we have to preheat the feedwater. Let's see here. What else do we have? 100% efficiency for the pump, 82 for the compressor, 86 for the turbines. All right, so a pretty long problem here. Let's start off here. So we will look at the gas side first. So we pull air in here, compress it, and then basically have it combust with something. Run it through the turbine, and then run it through the heat exchanger, and then we exhaust it out here at 12. So let's see here. We have, and then we have a feed coming off of here from the turbine that goes then back through the heat exchanger and preheats some of the feed water before it gets to the boiler here. Okay, so that's the boiler for. So let's see here. What do we have? We got a 300 Kelvin at 8, so it's air, so we'll use the ideal gas, and so we'll use reduced values to get a little better approximation. So we have about 300 kilojoules per kilogram is H. The reduced pressure is 1.386. We know the pressure ratio here was 11. So the reduced pressure at 9 is 15.25, which then gives us the isentropic entropy at 9. And from that and the efficiency of the compressor, we can figure out what the actual enthalpy at 9 is. At 10, we have 1100 Kelvin, so we can get the enthalpy, and we can get the reduced pressure. And then we know the compression ratio is 11, so we divide this by 11, so we get the reduced pressure at 0.11 here coming out of the turbine. That allows us to find the isentropic enthalpy at 11, using the efficiency of the turbine, we can get the actual enthalpy at 11. So now we move on to, when we have at 12, after it comes out of the heat exchanger, we know the temperature, so we can get the enthalpy there. Now, onto the steam side. Again, we can figure out the work into the pump and then the enthalpy coming out of the pump, as we've all been doing many times. And then again, the second pump, we can find the enthalpy in the specific volume, get the work put in by the second pump, and then get the enthalpy at 4. We know the pressure and temperature at 5 is 5 megapascals and 350 degrees C, so we can get the enthalpy and entropy. That allows us to get the isentropic quality factor at 6, the isentropic enthalpy at 6, and the actual enthalpy at 6 from the efficiency at 6. And likewise, we do the same exact thing at 7. So we have, again, the enthalpy at 7. We can now move on and look at get the ratio of the mass flows in the gas and the steam cycles. And so that's just looking at an energy balance on the heat exchanger. And we do that, we get that we have about 9.26 kilograms of air per kilogram of steam. Now we can do an energy balance on the feedwater heater, and we can figure out that we're bleeding off about 20.8% of the steam. So then we can go on to looking at the specific work, and we see that we have we can do an energy balance on the steam turbine and use the efficiency there. Again, I use I think these should be, let's see here, primes. 6 prime. This should be 7 prime. Yeah. Since I use the efficiency here. And now let's see here. We have we get the specific work out of the steam cycle, and then we can subtract off the specific work done by the pumps, and noting that not all of the fluid goes to pump 1. And so then we subtract that off and we get 764.5 kilojoules per kilogram. We can look at the net work in the gas cycle, which is this is the work in the turbine minus the work in the compressor. And then the total net work, so this is the specific work per kilogram of air, and this is specific work per kilogram of steam. So to get it on a basis of per kilogram of air, we need to divide this number by the ratio of the mass flow rate of the steam to the mass flow rate of the air, or multiply it by that factor. And so we get then a specific work out of the whole plant of 208.7 kilojoules per kilogram of air. Now we're given the power, the net power that was the net power that the plant puts out. So that allows us to then, I shouldn't have a dot here. Oops, where do I get rid of that? And that gives us the mass flow rate of air is 1,342 kilograms per second of air flowing into the gas side of the heater. We can look at the heat that comes in, and that's the heat that is basically from the combustion process that's heating the air up. And so we know the mass flow rate of the air, and we know the change in enthalpy basically from this inlet and the outlet of the combustion chamber. So then we get about 671 megawatts of heat flowing into the air. And we can then get the efficiency because we know what this was. This was given, and I can't remember what it was given as. Let's see here. You look back in the book. It was given as 280 megawatts. So 280 megawatts divided by 671 megawatts gives us a thermal efficiency of about 41.7%.